Welcome to this webinar on the climate emergency and how local authorities can use ground source heat pumps in their action plans and how we can help that lead towards zero carbon heating, in particular how Kensa can help you achieve that. The talks we have today, I'm going to do a very short intro on carbon emergency and how heat fits into that. Then we're going to have our commercial director for Kensa Contracting, David Broom, who's going to talk about shared ground loop arrays, what they are, how they work, and how they can be used for decarbonisation in social housing settings. Then we have Patrick Berry, who is the managing director of Together Energy Services, and he's going to be talking about how Together Housing are using ground source heat pumps and shared ground arrays across their estate as part of their decarbonisation agenda. Our third speaker is then going to be Iman Barmaki, who is our Director of Low Carbon Partnerships and was previously Head of Sustainability and Asset Management at Enfield Council. And he's going to be talking about how housing associations and local authorities can build business cases for green investment or how he can help social housing progress to get to those across the line. So he's had a lot of experience at Enfield Council getting projects like this over the line. So he's a great resource for you to use in the future. And then we'll come back in with the Q&A session with Stuart Gadsden. First of all, the carbon emergency. The statistics here from the Energy Saving Trust from a couple of years ago show how different types of our economy affect carbon. And you can see that heat in its various forms is responsible for about 37% of that. We're going to be focusing on the lower left-hand corner of that orange section, so space heating and cooling and hot water, which together represent around 21% of all carbon emissions across the UK. So far, to date, at least by our last count, 280 councils have declared a climate emergency, and now is the time to influence energy strategies and climate strategies across housing estates as the climate action plans are being prepared. We do get that chance to set targets, and it's pretty clear across most of the councils we've been working with so far that decarbonisation of heat has to be up there, and the setting of targets and objectives around that is critical to the path to zero carbon. Right now, only 6.2% of heat is from renewables in the UK. I've been working in renewables for 20 years now, and renewable heat specifically for all of that time, and we have made great progress, but you can see there's still a huge long way to go. Right now, around 20,000 or 20 to 22,000 heat pumps are installed per year, and the Committee on Climate Change have calculated that we're going to need 2.5 million installed by 2030 if we stand any chance of getting to zero carbon by 2050. So it's very clear that there's going to need to be a huge ramp up of at least 10 times our current deployment in heat pump installations if we're going to get anywhere near that. And then just a little bit there to say how Kensa can help you move forward to use ground source heat pumps and specifically shared ground arrays in your decarbonisation plans. So we can help all the way through from general education like this to supporting officers working on individual projects. And then we recognise that lots of different teams within authorities have to understand what's going on, from the finance teams to tenant liaison to the asset teams as well. So without further ado, David Broom, Commercial Director for Kensa Contracting, is going to tell you about shared ground arrays. Thank you.
Thanks very much, Matt. Yeah, hello, I'm David Broom, Commercial Director for Kensa. I'm going to be talking a little bit more about heat pumps, or ground source heat pumps specifically, and how we link them to what we call shared ground loops to deliver social housing retrofit projects, delivering fuel poverty reduction outcomes and reductions in carbon emissions. Just a bit of background on Kensa to start with, yeah, where we've got to, or how we've got to where we are today. First and foremost, Kensa started out as a manufacturing business around 20 years ago, started building ground source heat pumps from a small factory in Truro. This is back at a time when kind of carbon wasn't really, or carbon reduction wasn't really on the agenda, and oil and gas prices were such that there wasn't a huge running cost benefit either, but it was really the early pioneers in the industry that were looking towards heat pumps and the early adopters in terms of carbon reduction. And the business grew fairly kind of slowly and organically to start with, generally servicing the able to pay market. And about 8 or 9 years ago, we took a look as a manufacturer and decided that to scale up in terms of manufacture would be far easier to find opportunities to sell heat pumps in kind of multiples rather than selling bespoke solutions one at a time. So we did a few bits of business development, partly with the product in terms of the development of the shoebox heat pump. So we identified that all of the heat pumps that were available in the market were too large, both physically too big and too high in output, because buildings were getting generally smaller and better insulated. And the second bit of development was looking at the business. And as a manufacturer of ground source heat pumps, what we identified was that there were lots of large scale gas installing companies. There were lots of small specialist ground source heat pump installers, but there wasn't really a contractor we could align ourselves with to deliver ground source heat pump installations at scale. So we took the view to launch the contracting company as a sister company as part of the group. Slightly unusual for a manufacturer, but we kind of felt it was a necessary step to gain some traction in the market. Next slide, please. And one of the key things with heat pumps is the outcomes that you get are more dependent on the design and the implementation of the technology rather than the badge on the box. But because it was our badge on the box, we wanted to make sure that the design and the implementation was going well, which is the other reason for the development of the contracting business. And since launching Kensa Contracting, Kensa have led the supply of ground source heat pumps into the UK market, with that market share increasing over time, and generally to do with our kind of specialism on the kind of social housing retrofit and new build development sectors. Next slide, please. So before going into shared ground loops, always like to dwell a little bit on how the heat pump itself works, because it kind of helps to make sense of why we do things, how we do things kind of later on along in the slide. So with a ground source heat pump, in basic terms, what we're trying to do is gather a large volume of low-grade heat from an energy source, which is generally the ground. The ground loop, typically boreholes, but can be other forms of energy, gathers that large volume of low-grade heat and takes it to the heat pump and into the compressor. The compressor, as part of the refrigerant circuit, compresses that energy and it squeezes it and upgrades it to higher pressure. And as it does that, increases the temperature and then delivers useful hot water into the building. And the key with the heat pump is that the difference in the temperature between where the energy starts from, so from the ground, and where you're putting the energy into either radiators or into domestic hot water, the closer those two temperatures are, the less work you have to put into the compressor and the more efficient it becomes. And the general reason why heat pumps are a good idea is that for every kilowatt of electricity you put into that compressor, you get 3 to 4 kilowatts of heat delivered into the building. So that's where that COP or SCOP or efficiency of kind of 300 to 400% comes from, is that ratio of energy in to energy out. And essentially the refrigerant circuit is just a scaled up version of all the same bits that you find in the back of your fridge. If you imagine the inside of the fridge essentially being like the ground and the back of the grills at the back of the fridge being the heating circuit, it's the same process. Everyone has a fridge, everyone accepts that it works, but no one needs to understand kind of how they work in detail. When it comes to heat pumps, we tend to have to explain them a bit more, but the principles are exactly the same. So the initial premise for shared ground loop came about with the inception of the renewable heat incentive, and what we found was that the domestic RHI that was centred around kind of end users was great in that context, but looking at social housing providers, it didn't really provide the levels of term or the flexibility that we need for the types of application that we were looking at. And with the non-domestic RHI being paid over a 20-year period and having a slightly higher level of repayment, it was a more attractive route. It also provides eligibility for new build development as well when you go down the domestic RHI. But we looked at traditional district heating, which qualifies for the non-domestic RHI. We looked at traditional district heating and we found some issues really in that by having a central plant for developing the heat, you've got a couple of problems straight away. Firstly, you have to distribute that heat around the building or around the estate. And no matter how well insulated that pipework is, you're always going to have a loss to the building or to the ground, which someone has to pay for, and that generally ends up being the end user. You also have to heat meter and bill each end user for their energy use, kind of proportionate to their use through the heat network and billing regulations. And the issue with that is you have to have heat metering in place and a management and administration process to deal with all that. So then you have a cost of all of that. So you can get to the point where you're up to anything from kind of 150 to 250, 300 pounds per property per year in terms of administering and system losses before you've even used any heat. If you put a heat pump in the middle of that picture, it gets even more difficult because, as I said, what we like to do is run it as low a flow temperature as possible to maintain the efficiency of the heat pump. And by running a high temperature network, it means we have to run the heat pump harder to be able to deliver domestic hot water as well as space heating around the circuit, because the hot water system needs to be at a slightly higher temperature. So for all of those reasons and a bunch of others, we decided that we need to find a better way of attacking district heating using ground source heat pumps. And that's where the concept of shared ground loops came from, which is a concept we've kind of pioneered for the last sort of 7 or 8 years. And next slide, please. So with shared ground loop, what we do is we take a kind of a traditional district heat network and turn it on its head a little bit. We use the ground array where we gather the energy, the low grade energy from the ground that's used to deliver the energy to the system and make that communal. So we have a network of boreholes linked together via a central manifold and then distribute out to individual heat pumps within each home. This means that all of the energy that we're gathering is in a sense communal, and that allows us to qualify as district heating, but each end user has an individual heat pump within their home. This means that their billing is just naturally part of their domestic energy bill, because the heat pump is kind of downstream of the individual's meter. So the meter only spins when they're using heat and they're completely in control of the heat that they use. They're also then free to shop around for the cheapest form of electricity by switching energy provider, or they can go down the route of time of use tariff or 100% renewable electricity if they wish. So all of the heat metering and billing is removed as everyone just pays for their heat as part of their electricity bill. The other thing that does is all of the distribution system is on the cold side and not on the hot side of the heat pump. So this circuit will typically operate anywhere from kind of 2 to 6 degrees, but in certain applications can run up as high as kind of 10 to 15 degrees through that ground array circuit. But because we're operating at ambient temperature, as we flow through the ground between multiple buildings, or if we flow through a riser in a high-rise block, for example, we remove all of the system distribution losses from the system. So straight away, all of that extra running cost compared to a district heating system is removed. Next slide, please. So as far as possible, we've designed the system to mimic what people are familiar with a sort of typical gas boiler system. So you've got a network, an energy source within the ground that delivers energy to the building. And then we have an appliance within the home that upgrades that energy and provides it to useful heat that the end user kind of owns and pays for. So if we can run the video, we'll see if this one works. See if we can run the video on that one. Not today. Within the ground array, there you go. Within the ground source setup, where we have multiple heat pumps linked to a communal ground array, even the circulating pump that pushes the fluid through the boreholes is individual to each individual heat pump. So there's no central plant, there's no central pump pushing the fluid around the circuit. What basically happens is if on that large circuit, a single heat pump is calling for heat, that one little circulating pump within the heat pump has enough power to deliver the flow rate that one heat pump needs. And then as more heat pumps turn on, more circulating pumps turn on, and then the flow rate increases. And then providing that the design is done such that the combined head of all of the pumps operating can overcome the resistance of all of the pipes that are connected to it, we'll always get the amount of flow that we need dependent on the number of heat pumps that are operating. So it's essentially just acts as a naturally self-modulating system and does away with the need for kind of complex controls and any central equipment It also makes kind of service and maintenance and easier and removes any requirement for apportioning of bills. Next slide, please. Within the building itself, we have the shoebox heat pump, which I mentioned earlier. So the shoebox started life when the managing director about 10 years ago turned to the technical director and said, can you build me a heat pump that fits in a shoebox? What came out was more like the size of an industrial microwave. So it's about the 3 kilowatt versions, about kind of 500 mil cubed. Marketing didn't like the sound of the industrial microwave size heat pump, so we stuck with shoebox. But we do have to concede it is slightly bigger than a typical shoebox, but yeah, the name stuck. The appliance is designed to be as small and as quiet as possible and sits on the floor of an airing cupboard typically, with a shelf above it and a domestic hot water cylinder above that to provide domestic hot water. Small enough and quiet enough to fit, as I say, within a traditional airing cupboard, and the heat pump itself is actually a high temperature unit. What that means is when we circulate to space heating, the heat pump runs at typical flow temperatures of around 45 to 50 degrees, so slightly lower than a traditional gas boiler, but certainly hot enough to feel the heat coming through the radiators. But when we have a requirement for hot water, the heat pump switches to high temperature mode and then reheats the domestic hot water cylinder. And it'll typically do that in a kind of 1 to 2 hour slot once a day. And then you'll have enough stored hot water within that cylinder to provide domestic hot water to the resident. Generally, unvented cylinders are used, but in social housing retrofit applications, we can look to use kind of like-for-like cylinders. Either vented or Fortic style cylinders can be used if you've got low pressure hot water, or we've actually started a number of schemes recently using phase change materials, so a chemical thermal store rather than energy stored as hot water as an alternative. But generally the system's designed to fit within a single footprint within a traditional airing cupboard of the building. Nice and straightforward when we're replacing storage heaters, as we can take up the space that's generally used for the existing immersion cylinder. When we're replacing gas combi boilers, then we generally have a little more work to do to find place for the heat pump and cylinder. But within the context of kind of high-rise buildings and removing gas from those, it's the issues in generating that are outweighed by the benefits of the system. Next slide, please. So as far as the end user experience is concerned, you end up with a traditional wet heating system, so radiators with TRVs. The radiators will be sized around a 45 to 50 degree flow temperature. So what that means is we'll give the same amount of energy to the room as a radiator from a gas boiler, but we need to increase the surface area to compensate for the slightly lower flow temperature. So typically radiators for a ground source heat pump will be 2.4 times the size of a radiator used for a gas boiler. So that doesn't necessarily mean they're physically 2.4 times the size on the wall. It generally means we'll go from a single panel to a double panel radiator and maybe 20% bigger. And when we're replacing storage heaters, again, typically they end up being about the same size as the storage heaters replacing. We've actually had instances where we've made the radiators slightly bigger to match the size of the storage heater that's come out, just to avoid the kind of 40-year-old strip of wallpaper that ran either side of the storage heaters that came out. But as far as the end user is concerned, 50 degree flow temperature into a radiator, as I say, is definitely hot enough to feel the heat, but not so hot as to, you have to take your hand off it instantly. So it does provide a comfortable level of heat. In terms of control, we generally favour as simple as possible to assist with the handover experience. So just a simple twin channel time clock and thermostat, and we can specify the time clock and thermostat to match what's been used throughout the rest of your stock. Again, just to make it easier from a point of handover, and for TLOs and for call centre staff, if we're using familiar controls, it's much easier to manage both the installation and also post handover any controls queries, because the vast majority of initial issues that we get from the tenant point of view are related to controls. And if we have familiar controls to your kind of existing staff. It generally assists with that kind of first line of response to controls queries. Next slide, please. So in terms of the infrastructure that goes in the ground, the vast majority of projects that we install use closed loop vertical boreholes. We'll typically drill holes anything from 100 to 150 meters, but in a lot of kind of more dense applications, so suburban, urban settings, and again where we're looking at high-rise tower blocks, and we've recently been installing systems with boreholes from kind of 200 to 220 meters in depth. So in the context of a 13-story tower block, we're about 4 to 5 times the height of that block vertically downwards around the outside of the block, just to give everyone an idea of scale of what that 200 meters looks like. The reason closed loop boreholes are preferred is, one, generally there isn't space to look at horizontal arrays, and it's a much easier thing to quantify at the kind of pre-design stage. Closed loop boreholes are fairly kind of stable from a design point of view. We can look at the existing geology and get a fairly accurate view on what the borehole depths are likely to be required, kind of before going into too much detail in terms of design and feasibility. Next slide, please. So hopefully if these videos work, we'll show you a little bit more about how the drilling operates. So this is a typical mid-sized drill rig on a social housing retrofit applications. This is actually one of the first shared ground loop installations that we did going back 6 or 7 years ago, but the borehole installation process remains pretty much unchanged. The drilling rig, we generally use a mud flush technique for drilling. So the drill rods that you see on the left-hand side are hollow. We pump kind of muddy water down through those holes, and we flush out the hole as we drill it and bring the risings to the surface. And as we do that, we bring all the mud that we've cut away from it. It's pumped away into a mud puppy, and then it's filtered and is recirculated through the hole to keep the hole flushed. And then on the right-hand side, that just shows the probes, 40 mil MDPE pipe work that's just kind of pushed down through the hole that we just created, and that's the probe that's used to take the energy. Yeah, that's fine. Next slide. In terms of other energy sources, as I say, typically most installations will use closed loop boreholes, but we can use water from the ground. So in terms of aquifers, if we've got water close to surface that we can use and we can get the flow rates required, we can use what we call open loop, so water from the aquifer. And that video seems to have stuck. We do also have alternatives for either using mine workings, and there's a lot of interest at the moment in exploring the latent energy that's available within mine water kind of throughout the country. Statistic I saw the other day was something like 25% of the UK could be heated from the energy that's stored within mine workings under towns and cities in the UK. We can also use surface water, so kind of lakes and rivers, or potentially even seawater. We've looked at some schemes along those lines. Okay, so the videos have finally caught up, but hopefully that gives you an idea of visually what I was just talking through. And then above ground, the same thing happens. We have a network, an ambient loop of antifreeze that connects a number of buildings together to be able to develop that energy. So hopefully that'll allow us to move on to the next slide. Excellent. So once we've delivered the energy, we can then distribute it around the building or the estate. Generally, the boreholes will link together via a subterranean manifold, which has a standard kind of manhole covered lid. And generally, that's the only visible evidence that we've been there after the installation is that manhole cover lid. So everything else is kind of covered up under the ground. The boreholes are terminated 1 meter below the surface, and then we kind of trench into the manifold and put the connecting pipework in and backfill to level. So one of the nice things about doing case study visits, we take people out to see sites that we've installed previously, showing them around the outside of the buildings, and yeah, not being able to see anything. There's no visual evidence that we've been there after the installation. Next slide. This just shows schematically on a typical installation where we've linked 3 boreholes together and then distributed out to 3 heat pump locations. This particular one was actually a new build, so we were able to go under the slab of the building. But generally on retrofit, we'll come up surface mounted, either on the outside wall, or maybe we might even go all the way up to roof level in through soffits and then drop down into cylinder cupboards. But the benefit of having all the distribution system on the ground side means that we've got lots of flexibility in terms of how we connect these heat pumps together. Next slide, please. And this just shows the same thing in section as we've connected to multiple heat pumps on multiple floors via the ground array. Next slide, please. One of the other benefits of having the distribution system on the cold side of the heat pump is essentially we've got a chilled water infrastructure arriving as far as each property. Again, probably more relevant to new build than retrofit. Moving forward, we can see certainly in new build properties, the issues around overheating becoming probably increasingly an issue compared to underheating in winter. So by using a heat pump, we can use that chilled groundwater infrastructure that reaches each property, bypass the heat pump and provide what we call passive cooling into the dwelling. So an interesting one if you're looking at new builds potentially. The other key thing, again, is when we're looking at multiple story buildings, kind of high-rise tower blocks, is compared to traditional district heating, that infrastructure is on the cold side. So we remove all of that heat loss. So we remove any issues with regards to kind of overheating of risers, corridors in summer where we've got waste heat coming from the pipework. Next slide, please. So in terms of compliance benefits, you know, the carbon savings are significant. So now SAP is being updated. So the next version of SAP, when we get into SAP 10 or SAP 10.1, will show a much more updated carbon factor compared to the current version of SAP. And it's actually kind of reducing further again. But even assuming 233 grams of carbon, kilograms, sorry, of carbon per kilowatt hour of CO2, we look at typically 60 to 70% carbon savings versus either direct electric or versus gas, because of the efficiency of heat pump and because of the relative carbon intensities of electricity and gas. So significant carbon savings to be had. And obviously as the grid further decarbonizes, those carbon savings increase in the future. So by putting the heat pumps in now, you're kind of not only kind of saving carbon day one, you're actually putting the dwellings onto a path to zero carbon as the grid intensity falls even further. Right now, a lot of benchmarking is done via SAP, and generally the installation of a heat pump will see a SAP improvement probably of only a few points, maybe up to 10 or 12 points where we're replacing direct electric. But that's generally because they're using sort of running cost as a proxy for carbon on the actual SAP score itself. Whereas if we look at the actual carbon intensity, so if you look at the environmental impact rating, then you see a much more pronounced reduction for the heat pump compared to either gas or direct electricity. In terms of additional benefits, we also have no combustion, so there's no flue or ventilation requirement around the heat pump, so it can be boxed in completely, and externally it removes any visual impact on the building in terms of flues, and that's particularly relevant obviously on high-rise buildings. And also compared to gas, we're removing all local emissions of NOx and SOx around the building. So again, a benefit in terms of local air quality. Final one in terms of service and maintenance, as I mentioned, the heat pump itself, the refrigerant circuit itself, a bit like your fridge at home, doesn't require any service and maintenance on an annual basis. It's charged at the factory, and the refrigerant circuit is set to run for the life of the heat pump, which is deemed to be you know, anywhere from 20 to 25 years. But outside of the heat pump, you do have traditional kind of wet system kind of service and maintenance to take care of. So ensuring pressures are holding through the system, pumps are spinning, valves are moving, controls are operating. So it's really a visual check on all of those elements that are required, but there's no mandatory requirement for a service or an inspection on the heat pump itself. And even if you wanted to, there's nothing you can do to kind of in terms of preventative maintenance or kind of performance consistency in terms of maintenance to the heat pump. So there's little to be done there. Next slide, please. So in terms of Kensa, what we can offer, Kensa Contracting as a delivery partner can assist at early stages of development with kind of early stage design and costs, providing budget prices and outline business cases. We can provide with initial feasibility around kind of the ground and the geology, ensuring that the conditions are kind of safe and adequate for drilling. We've got the space required to install the necessary ground array that's required for the installation, and then we can go on to deliver a full kind of turnkey package in terms of the design and implementation of the ground array, all of the connections, heat pump installation, wet system upgrade, all the way through to handover, including tenant liaison, which is also a key part of the installation from a social housing retrofit point of view, and educating tenants in terms of what we're doing, why we're doing it, how it's scheduled, what the impacts of them are going to be, and the benefits to them on the system. But Patrick's going to go and talk about that in a little bit more detail with relevance specifically to some work that we've been doing with Together Housing. So I think I've gone over a little bit, so apologies for that. I do tend to rattle on a little bit when I get on subject, so hopefully that's been of interest and of relevance to everyone. I look forward to picking up some questions at the end, and I will pass now on to Patrick. Thanks very much.
Thanks, David. I'm Patrick Berry. My job at Together Housing is to be responsible for our investment into renewable energy, and I'm also responsible for the development of our carbon reduction strategy. Next slide, please. So just a little bit of background. Together Housing has about 37,000 properties across Lancashire and Yorkshire. And we have a strong commitment to decarbonisation and indeed social value. But like other housing associations and local authorities, we're confronting what achieving net zero carbon means, certainly in terms of investment costs, to the business as a whole, in terms of how we operate, and to our tenants. This is especially the case as most of our stock was as a result of stock transfers from local authorities with whom we maintain a close working relationship. And I think all of these local authorities have declared climate emergencies with target dates in advance of the UK's government commitments. And of course, they look to us and ask us what it is that we are going to contribute towards meeting those targets, which range as low as 2030. And so within that, we have recognised that the decarbonisation of heat is a really key and essential component of our decarbonisation programme. In fact, it's the major impact that we can have and control. And as David already said, its real value comes as the grid itself decarbonises. And so over the last 8 years, the carbon element of the grid has dropped by 50%. And that's only going to get better as time goes on. So as more and more of our properties convert to renewable heat in the form of heat pumps, as the grid decarbonises, we get closer and closer to achieving a net zero carbon position. In terms of how we got to use the heat pumps, so stay on this slide, we have a key concern. In fact, we came at this really not from a decarbonisation perspective in the first instance, but from a very practical perspective, in that we had some very vocal resident groups who had complained for a long time about night storage heating and its ineffectiveness for them, particularly as that related to flats and tower blocks. And this is more anecdotal than statistical, but that was affecting how long people stayed in properties and on people's health, and the overall turnover rate that we were seeing in some of our worst affected properties. And I'm sure you'll be familiar with some of the comments you received. If you have the next slide, please. So speaking to tenants is very common sort of comments, and to summarise those, systems of night storage heating are not centrally controlled. They're very difficult to operate, where you have to control both how much heat's going in, how much heat's coming out, probably 24 hours in advance. If it is cold, they tend to run out of heat in the afternoon. And if you choose not to use them and put another form of heating, they can be extremely expensive. And indeed, we found that many tenants didn't use storage heaters at all, and instead they bought supplementary heating, often in the form of oil radiators. And of course, they run those in the day on economy 7 at peak power rates, so it becomes very expensive. And at the other end of the spectrum, they didn't use them at all and often sat in the cold and suffered for it. Next slide, please. So our main aim was to make sure that we didn't have a quite large group of properties where the cost to live in them and heat them properly for the well-being of the people living in them was significantly more than another group. And obviously what we're comparing with here is most of our properties having gas central heating. So alleviating the fuel poverty that arises from that is not only good for our tenants' well-being and quality of life, but also contributes to a kind of net exchequer benefit, in some cases reducing premature death, but certainly reducing the cost to other public services, particularly the NHS. Next slide, please. This wasn't totally driven by a tenant consideration. There's also a strong business case for it. Most of the night storage heating, as we said, was in flatted properties. These are not our most popular properties, and if we want to keep them sustainable, they need to be affordable to live in and they need to be comfortable to live in. And if we don't do that, then the long-term viability of these assets is certainly likely to be affected. So what we tried to do in picking this up with Kensa well over 2 years ago now, was to look at how we could use the renewable heat incentive, and in some cases eco, where it was available, to at least get our money back in terms of investment, so that over a 20-year period, our capital injection would be returned. And to test this out and to test the actual practical implications of delivering a fairly invasive scheme, we identified 2 tower blocks in Halifax, both 6 stories high, and about 62 units in each one, mainly occupied by the over 55s. We identified these properties particularly because the tenants have been particularly vocal and organised about the failures of the existing heating system. And so we were to some degree pushing in an open door in proposing a new heating system. Nonetheless, we wanted to understand better the whole process of tenant liaison and how we get across this fairly major change in how the systems are going to work, but also the kind of large-scale drilling that's going to take place outside the property, and really understand, as these systems were installed, how reliable they were and the extent to which they could provide the heat and hot water required and make that comfort leap that we were looking for. And the idea was, if we could see that this worked from all those perspectives, from financial and for the tenants, from the practical implementation, we would look at taking forward a much larger programme of implementation across similar stock, and probably targeting at least 1,000 properties. Next slide, please. As has already been alluded to, we were happy with the pilot. It was certainly very well received by the tenants, and somewhat strikingly, they take a great interest in the drilling that takes outside the property, rather than it being a distraction. And bearing in mind that we had to close car parks and close green space, it was particularly well received. The subsequent implementation of the scheme and the operation of it has proved it to be cheaper and warmer, and has been very reliable in terms of the feedback we've had. I'll touch on that a little bit later. So while there were some teething issues with tenants who forgot how to use the timer, etc., we were able to put in place customer service responses to address this, and Kensa were part of that solution as well. And we've subsequently progressed to a much larger programme, which is underway now, and it's been underway for the past year or so. We have 473 systems currently in, and in 2019, my understanding is that contract accounted for approximately 10% of the domestic ground source heat pump market, so quite an impact. The way we approach this on an ongoing basis in managing the programme with Kensa, each individual scheme is appraised separately to look at whether it meets our criteria in terms of washing its face over the 20-year programme, and whether or not it can get eco and any other special costs that might be associated with it. We also look at that as an overall programme. So we're looking at this in the round, and we can also consider the counterfactual cost, because at some point the existing night storage heater assets would have had to have been replaced. So we do that for each one, signing off each particular scheme as it comes forward. Next slide, please. And just as a sort of tail end to that, we have just about to start something different, which is 3 tower blocks where there is a gas heating system in there. So that will be something of a different challenge, because obviously we don't have some of the advantages of taking out night storage heaters. And so that will be another dimension to this, but obviously post-Grenfell we're pretty keen to take the gas out of those properties for safety and compliance terms. So, to sum up from the initial projects we've done so far, tenants are not put off by the nature of the works and the borehole hole drilling, and we find them certainly ready and able to accept the change that's being made for the positive. There's a strong recognition, and certainly post-submission, that they have an affordable whole property heating that they can control, which for night storage heaters, or people who've had night storage heaters in the past, is a revelation, I think. What we did in the pilot as well is we were able to get smart meter data from a sample of properties to look at the actual running costs in each of those over the course of a full 12 months. And they made, on average, around a 45% saving on their energy costs. And so we moved from something in the region of £1,000 for running heat and other power in the property to £613 on average. So quite a big difference. The system faults we've had to date have been minimal, and as we can see from this slide, tenants were all too keen to thank the contractors for the way in which the process was delivered, which is always nice to see. Next slide. From a Together Housing perspective, well, we have a scheme that deliberately uses the available incentives to pay for itself. We are in the business of managing long-term assets, and so the 20-year payback is not a problem for us, so long as we've got access to the cash to finance it up front. Critical to this was Kensa's management of the applications to the renewable heat incentive, which certainly on the non-domestic side is complicated, to say the least, and also eco on our behalf. So that is all done and effectively delivered to our door. We have a measurable reduction in our carbon impact on those properties, which will be long lasting, and significant improvements in comfort and affordability, which should make them easier to let in the long term. We also deliberately put in place a system of training for our internal repairs team, and that has worked well, and they are able to both service but also change out the pumps where needed. One of the key reasons we were positive about the heat pump is that it can be relatively easily removed and replaced with another, enabling the pump to go away to be fixed, but the tenant not to have the disruption of no heating and hot water for an extended period should it go wrong. And overall within the organisation, because this was something that was done as a trial and was not mainstream, is I think we've managed to demystify heat pumps as a technology and soften the ground significantly for that transition to the mainstream, which has to be part of our decarbonisation programme. Next slide, please. So I think over the last couple of years we've demonstrated that ground source heat pumps can be managed and delivered at scale and across a wide geographic area. Our sites are really quite spread out across the north of England, and our next major challenge is how we transition away from gas heating in our houses. And we see certainly heat pumps being as a major part of that solution. I think the key to this for me is that the social housing sector as a whole has both the scale and investment power to drive this transition away from fossil fuels to renewable heat, to create the supply chains and the scale which will ultimately reduce costs for us all to roll this out. In other words, to act as a kind of market maker which sets a tone. And I think the government, in some of its narrative, is looking for us to do that. Next slide, please. So just finally, the use of heat pumps provides social housing providers with the chance to innovate because there's an awful lot going on in terms of particularly the electricity grid, which provides opportunities. I think those opportunities lie, and these are areas we're actively exploring, in how we, through the installation of heat pumps and smart thermostats and other pieces of energy technology, we'll be able to shift to the digital management of our assets, which allow us to see what's going on in the property, the behaviour of the tenants in terms of the heating, the humidity, the occupancy, internal temperatures, etc., which allow us to have much more predictive repairs. They also allow us to have a higher level of safeguarding for tenants with automated alarms for low heat or even extreme heat, where we think that is going to be an issue. But in terms of the business case, the heat pump assets at scale, it is possible to aggregate those up, and working with aggregators who work themselves with the grid, heat pumps can be brought into play to help balance the grid. So taken the demand from those heat pumps taken off grid at key parts of the day, as long as sufficient safeguards are in place. And we would do that because that has the potential to generate revenue from doing so, and also help balance the grid. Even where there's too much renewable power coming into the grid, you get on some sunny and windy days, there'll be opportunities to take power off the grid and to put that into the hot water tanks or into the heating systems as required. So we see that revenue as part of our long-term solution, as part of our business case. But overall, the energy technology and data collection is all moving very quickly, and we see that as being part of how we think about future installations and how they knit together, not as individual installations in properties, but as a network of energy assets, which we can both see, monitor, and can control in various ways. And I will leave it there, if that's okay, and I'll hand over to Iman Barmaki, who is the Director for Low Carbon Partnerships at Kensa and supports local authorities to develop their business cases. Thank you.
Thank you, Patrick, for sharing your amazing case study, and good afternoon, everyone. So we're coming towards the end of the webinar now, and you have me for a few minutes, so I'll try to be brief and get to the 5-minute deadline. So my experience is working strategically with local authorities to build business cases on large-scale projects. And some of you will remember me from working with Enfield Council. There we managed to invest approximately 50 million into retrofit renewable energy projects, including the largest installation of ground source heat pumps in social housing in England. One of the key techniques which I've always used is to seek to highlight added value benefits of any investment upfront. And this is always key into engaging your stakeholders, decision makers, and politicians. It's also worth recognizing that many different local authorities have different ways to develop business cases, and the ones that I've worked with in the past have all created internal business case templates, which are to kind of meet the needs of particular teams, usually procurement and finance, and those decisions are often based on competitive pricing. Whilst it's a great way to reduce your costs, it's not always in the best interest of social value, national policy, and sometimes even social equality or financial inclusion, which are ever more important. And it's important to find that kind of happy medium in between. So what you can see on your screen is basically Her Majesty's Treasury has a business case guidance model called the Green Book method. And this provides a good standard framework for preparing business cases for spending proposals in the public sector. I certainly have used this to drive investment cases in the past, and it's been fairly successful for me. Green Book business cases, they're prepared according to the model which you see, which is the 5 interdependent dimensions. And this is called the 5-case model, and I'll briefly outline the 5 cases. So we always start with your strategic cases, and here we need to think about what's the case for change, what's the rationale for intervention, and moving away from business as usual. For the purposes of today, this can cover a number of key national policy commitments, such as net zero targets, also the electrification of heat, which has been mentioned, and which takes advantage of the increase of renewable electricity supply on the electrical grid. Also recognizing that there are other policies coming in the future, such as the Future Home Standard, which is moving away from fossil fuel powered heating. We also need to be able to link this to any action plans which have been developed off the back of the local authority climate emergency declarations. So all of those are really important to put into the strategic case. In terms of the economic case, the questions we need to think about here is what's the net value to society or social value of the intervention, again, compared to business as usual. What is the impact of reducing fuel poverty? That increased availability of spending power for residents who have been lifted out of fuel poverty, can this lead to local economic growth? Equally, the impact of the environment needs to be featured here. So local air quality improvements leading to better health, less strain on the NHS, even more important right now. And this leads us into the commercial case. And, this you need to find a realistic and credible commercial deal to strike, and who's going to be affected by this. And this is really where your procurement aims come in and your commercial arrangements relating to any services or asset come in. And at this point, it's important to mention that Kensa is the #1 provider on a multiple well-known OG compliant procurement frameworks. And that's something that needs to be built into the business case in terms of what your procurement strategy might be. The financial case, now, what's the impact of the proposal to the public sector budget in terms of both cost of capital and revenue? And this is typically concerned with the net cost of the public sector. So if a proposal is adopting a cash flow statement, this needs to be over the lifetime of an asset. And I find that 20 to 30 years is probably the kind of time frame that you need to do any cash flow statements. We also need to take into account all of the financial costs and all of the financial benefits that arise. So you need to include grants, reduce maintenance costs, compliance costs, the financial value of carbon saved over the life of the asset. And also it's important to have an understanding of how do we value that carbon internally within the local authority or social housing sector. Also, the ability for reduced cost electricity is quite important. So, with the introduction of time of use tariffs, you can build this in. And, we cover affordability within this sector, whereas the economic dimension, which has been covered previously, kind of assesses the drivers for best social value and affordability to residents rather than affordability to the local authority of the social housing organization. And finally, is your management case. Are there realistic and robust delivery plans in place? Can the project be delivered? Can internal council or social housing teams be trained to manage assets and have good asset management principles in place to look after these? These are basically all of the questions that we should all be asking if we're looking at the different aspects of a business case and bring it together to make sure we capture all the benefits and the importance of the investment into the future of our housing stock. So I hope that's been helpful. And if you have different ways of developing business cases, I hope you can have some takeaways from this slide, which you can incorporate into your internal processes. And finally, what I just wanted to say that at Kensa, with our approach with our clients is to establish more of a partnership feel. So feel free to contact us, discuss any different aspects that you might be working on, and any support you might need to feed into any delegated authority, cabinet reports or investment reports. So thanks for listening. I'll hand back now to Matthew for Q&A session.
Lovely. Thank you to our three speakers there. I hope that's given everybody a really good overview on ground source heat pumps in general, ground source specifically, and even more specifically, ground source with shared ground loops. We have loads of questions come in. It's been really fascinating seeing your questions, so thank you for submitting all of those. Stuart and I have decided we'll do a short few minutes quick fire on the technical questions that have come in, and then some of the more funding and decision making stuff we'll hand back out to our panelists. So Stuart, do you want to take the first one?
Well, I was just going to ask them to you, Matt, because I'm going to put you on the spot.
Go on then.
So, question one, can the domestic hot water supply temperature be reduced from 60 degrees?
Yes, the hot water cylinder has a thermostat which you can set at any temperature. It's normally 60 degrees to ensure Legionella protection, but you can also then blend down to any temperature after that, either leaving the cylinder or at the point of use at a bath or a shower or a tap or whatever you're using. So yeah, 60 is just the maximum really you're going to get.
Excellent. Can you provide links to some examples of the radiators that we use?
Yes, we just use normal off-the-shelf radiators, nothing special. So Stelrad, Dimpex, whatever you want to use, you can put on. The only difference is in the sizing. So we size them for the flow temperatures that we're going to use, which typically 45 to 55 degrees, depending on the install. And as David said, if we're running at 50 degrees, they'd be 2.5 times the kind of standardized rated output. But other than that, you can use your favorite brand.
Does the cylinder contain a buffer store?
No, it doesn't. The cylinder is typically just for hot water. Most systems, if you're careful in the design and particularly the radiator control, you can get away without a buffer store at all. If we're going to start to do some of the demand side management that Patrick was talking about, then we will need at some point to get the best out of that, to have some sort of storage in the properties. We think that's possible to do with water. It's more likely to be used once we start getting the phase change storage, because they just physically take a lot less space. So yeah, we're working on storing for load shifting, but for just simple operation of the system, you don't need a buffer.
What is the lifespan of the borehole pipework?
The borehole pipework is a plastic material called HDPE. It's the same pipe as you see in water supplies to properties and gas supplies to properties. Expected lifetime of 100 to 120 years.
Can you advise the approximate life of the heat transfer fluid that circulates within the boreholes?
Yeah, if any of our suppliers of heat transfer fluid are listening, then apologies, but I think they would like you to replace it every 10 years. It has antifreeze in it, plus also corrosion inhibitors and biocides and things like that. And they would advise everyone to change that every 10 years. I know most people, it's more like 20 years. So if you imagine flushing it around every 20 years or so, that would probably be a fair bet.
Okay, two more, Matt. How do the two ground loop systems, borehole and trench, compare in efficiency and cost, assuming land is available?
Yeah, efficiency is the easy one because they're pretty much both the same, but that's also artificial, because once we've decided on the type of collection system for a particular project, we'll design it to give a particular performance back to the heat pump. So we almost design out any differences between them. The horizontal ones, by their nature, take up a lot more space. The vertical borehole, because we're extracting heat, you imagine, from a cylinder around 10 to 12 meters in radius around a borehole, you can actually get a very large volume of ground to take heat from, compared to a horizontal arrays going in about 1.2 meters deep. To get the same amount of ground, you need to cover a larger area. Most of our work with shared ground loop arrays is vertical boreholes, because you are looking at that higher density housing, aggregating properties. I think we've probably done one or two in the last 5 years of horizontal arrays. That's not to say private housing, individual horizontal arrays are quite popular. I even have them in my own house. got space for it. So.
And then final one for this quick session of Ask the Expert. What is the average temperature of the supply pipework going up the risers?
Between 2 and 8 Celsius. So at the end of the heating season, after we've been taking heat out of the ground all winter, it will be down to around 2 Celsius, and it will rise up to 8 by the end of the summer. It can be a little bit wider than that. If you had a really, really cold winter, sort of 1 in 50 sort of cold winter, you could drop a little bit below 0. And if you had a really warm winter followed by a mild summer, you could get them up to 12 or even 14 degrees, but 2 to 8 typically. Okay, hopefully that's the quick fire ones.
That's the quick fire ones for now. We've had a lot of questions related to RHI, unsurprisingly. And so I thought I would take that issue first. And I think this will be suitable for all panelists, because some people are also interested on Patrick's view. So I guess to try and summarise all the questions, what is our view on the UK government support for heat pumps as part of this low carbon heat transformation? In particular, as the current plans for life after RHI and the recent consultation appears to rule out large scale support. You just have a comment on how currently it interacts with domestic and non-domestic RHI. Patrick's views, I guess, on these impacts on Together Housing and the future for his ground source heat pump schemes, and a little bit about the RHI new build retrofit projects and anything moving forward on that. So hopefully that's covered most of people's questions around RHI, and I'm sure David and Matthew and Patrick and Ivan have some good thoughts on that.
Okay, could I ask Patrick to start us off, just outline your thoughts on the RHI and how it affected your decision making to date, please, and then maybe David or Iman to pick up some of the more technical bits of that.
The RHI was instrumental in our decision making to go ahead with the programme. It kind of seemed a no-brainer to us to be able to take out a very inefficient, disliked heating system to replace that with one which gave us whole house heating at a much cheaper price and more comfort for the tenants. We had to be able to have access to the cash to do that up front, but that's fine. We could do that, but without the RHI, I don't think we would have done that. Going forward, we are obviously looking to get as much of our programme done within the current RHI window as possible, and securing our position in relation to that. But we would very much be looking for similar kind of support going forward from the government to enable us to continue with that programme, because of the nature of ground source heat pumps and the amount of work required to install them. Doesn't make them more expensive, but you get greater benefits from that. So we would be looking to help put our pennyworth in to lobby for that to continue, perhaps around the government's certainly manifesto commitments to the Social Housing Decarbonisation Fund, which might include some commitments to that. Thank you.
Lovely. And then David, maybe a little bit on what we know so far about future funding, which not a huge amount, but we do know a little bit.
Sure. Yeah. We're a bit disappointed with the outcome in seeing the consultation after the March budget, where the announcement for a 12-month extension to the domestic RHI was given. The non-domestic RHI was a bit conspicuous by its absence, and we thought that was just a logistical delay. But it turns out that actually they thought they would help by launching a consultation 6 months ahead of the end of the scheme, rather than giving any form of longer-term certainty, which definitely hasn't helped. And what the consultation basically says is short-term, they're extending the window for the end of the RHI in 2 ways. One is for any installations that can be started but not completed before the end of the RHI, which is 31st of March 2021. We can make an application and then we can modify capacity, so we can add additional heat pumps after the deadline and then still receive RHI income from them. The limitation there is, as I say, we have to have heat pumps installed, commissioned and RHI applied for prior to that deadline. And the second route is what's called tariff guarantees. And the tariff guarantee route basically allows you to pre-apply for the RHI before starting the scheme from April 21 onwards, but having until April 22 to complete the installation and the commissioning of the scheme. The tariff guarantee route only kicks in on installations over 100 kilowatt, which for us isn't as helpful as they thought, because whilst lots of our schemes in total achieve greater than 100 kilowatt, we generally configure them in lots of small clusters of ground arrays, typically kind of 2 to 12, 15 properties per array. So we don't meet that kind of 100 kilowatt requirement. So it's not as helpful to us as they thought. So we've gone back and we're lobbying hard for better outcomes, but the close to that consultation won't be until kind of after the summer. But certainly if anyone else wants to respond, kind of prompting a slightly more helpful response for heat pumps in general, but shared ground loops specifically, that would be great. And we'd be happy to help inform any of those responses if anyone wanted some assistance with that. And essentially that's all we know. The other thing they've hinted at is there will be other forms of support. So there's a clean heat grant, which is also having a consultation, and there's also the social housing decarbonisation fund, which has a much larger pot available to it. So we're hopeful of eligibility for that. But unfortunately, the situation that we've been explaining to BEIS for probably 5 years now is that the one thing we can't have is short-term uncertainty, is exactly what they've kind of delivered to us. So I wish we could give a much kind of more definitive and clearer picture right now in terms of what the shorter term outcomes are from a funding point of view. But long term, all of the big picture stuff and all of the nice words say, yes, we need lots and lots of heat pumps going in. So you know, we're hopeful that we'll get some positive outcomes from the consultation. I think we're planning on perhaps having a follow-up webinar, a second session, kind of specifically on funding and the future of RHI, just to delve into it in a little bit more detail if there's an interest.
And I don't know if you want to add anything to that, Iman, on ways that we can see developing non-subsidised systems. We appreciate it's going to be a few years ahead yet, but just if you had any thoughts to share.
Yeah, I think it's important at this point to recognise that the RHI is going to be a big barrier, and that is a huge problem for the industry across the whole renewable sector. I think there's the potential for local authorities, social housing providers, financial institutions, and the private sector to potentially develop different types of business models. They're very difficult to develop. Some have already been developed for running district heating networks, and district heating networks, you know, we've discussed this to a certain extent, and those processes can be time consuming and can be costly. So one of the things that we need to bear in mind is that's something we can develop potentially to help, but right now the policy area which we need to influence the most is to lobby government and say that this is definitely needed, so that actually clients like Patrick and also Enfield, that decision making and that business case development process can be a lot quicker and can develop faster and ultimately help us all meet our decarbonisation aims.
Thank you.
Sorry, Matt, can I just, finally, there was a couple of specific questions just on RHI, if I just kind of head those off as well. So one is between the non-domestic and domestic. So shared ground loops qualify for the non-domestic RHI as they're considered district heating. So if you go onto shared ground loops, you wouldn't be eligible for domestic RHI based on the current regulations. And in that same way, the domestic RHI new build developments aren't eligible for the domestic RHI, but they are eligible for the non-domestic RHIs covering district heating. So that way, using shared ground loops under non-domestic RHI is eligible for new build developments. Sorry, Matt, I'll leave it.
And I think the last technical one was on the closing dates, which I think you've covered reasonably well in your tariff guarantee and extending. Okay, sure. Can we have the next ones, please?
Yep, this one's probably specifically for Patrick. So it's comparison figures for pre and post installation energy costs. any insulation upgrades that have been carried out to any of the flats? And did you consider high heat retention storage heaters instead of ground source heat pumps?
Yes, starting not necessarily in that order. When we first proposed the scheme, we did a piece of research internally which looked at the existing capital life of all our night storage heater assets. We looked at at that point in time the other options that might be used to replace them, both in terms of their heating capacity, but also cost, but also any potential funding that was available, and also the carbon impact. And we reached the conclusion from that with the RHI support, the switch to a heat pump provided us with the best option, giving us full controllability and whole home heating in the way that it does. We do have a position, and we have a link through to Eco as well and elsewhere, that if any of the properties we find does not have sufficient insulation to make the calculations for the heat pump work, that will be remedied before the installation takes place as part of the site planning and project planning we have in each case. So it's very much part of our equation, and we work closely with Kensa and other partners to make sure that's delivered. And finally, I talked about a little bit of the comparative heat costs. It is quite difficult to collect. What we did was we took a sample of what was originally 8 tenants who were all with Utilita, because we have a relationship with Utilita. The tenants agreed to share their data, and we tried to get some pre and post. Unfortunately, all the pre-costs moved out before we could collect them, or passed on. But we did have 7 different properties where we had 12 months data on the running costs. And so we were able to get those very specific in terms of the whole running costs for the properties, which includes cooking and all the other things that people plug in to the grid. And so on average, we were talking about 450 quid for the heating and hot water for the entire year, which we were very comfortable with. Thank you.
Thank you, Patrick. That's well covered. Stuart, I've got another one.
Yep, always an interesting question, this one. Can the panel give some guidance as to how much the systems actually cost to install? Payback, I think, has kind of been covered with the RHI, but also looking at life cycle costs as well.
Okay, I think we'll put that one out to David Broom, if you can, please.
Sure. So obviously the cost is dependent on application, and there's a number of variables. So it'll depend on kind of ground conditions, but also the size of the scheme, the density of the scheme, kind of high-rise blocks. Obviously, we need to fit more boreholes into one location, so we've got a greater density of boreholes. So there's a number of design variables that come into generating the price. To some extent, kind of what fuel's being replaced as well, will also feed into it. But to give a range, I would say typically we're looking at anything from for a retrofit application and looking at a kind of a turnkey solution, so design, delivery, all the way through to handover. We're looking at typically anything from around £13,000 up to kind of £16,500, £17,000 per property as a capital cost of installation. So it is a significant investment in terms of payback. Right now, the RHI kind of tracks about kind of break even. So across those property types, we'd normally see the RHI deliver funding of anything from kind of 14,000 to £20,000 per dwelling over the 20-year life, which is paid quarterly and index linked over the 20 years. So that's a fairly typical range of kind of costs and paybacks that the model is using at the moment.
Lovely, thank you. Next one, if we can.
Yep, this is a very good question. There's a lot of push for ambient loop communal heating, except not necessarily using the shared ground source that we are doing, but using an ambient loop heated artificially. So, for example, from our air source heat pump in our plant room, the understanding of the question is that these solutions will be caught up by the metering and billing regs, and then obviously any subsequent consumer protection regulation. And is that the view of the panel as well?
Yes. Shall I take this one? I think yes. It's definitely cheaper to have an air source heat pump powering the ground array, and I have seen some solutions where there's a ground source heat pump powering the ground array separately. I believe it does fall under the European metering and billing regulations. You're generating heat that's not kind of just naturally occurring in the ground elsewhere and distributing that around. So even if it's at 20 degrees, my personal opinion is that should be metered, and it does vary depending on how people decide to heat their homes. There are some subtleties with that. For instance, the way it's treated in SAP and other calculations, there's a million variations with that. There's one thing for sure is that does take energy, and it does take some cost to run whatever that appliance is. And actually, the question was about air source and ground source powering it, but you could make the same point about just an air handling unit or waste heat, or all sorts of different ways of doing it. You could even put a gas boiler on it if you really were so motivated, which we aren't. But that cost has to be shared back to the end users in some way. Deciding a fair way of doing that is quite tricky. So we've decided that the shoe boxes are perfectly capable to accept temperatures from -5 right up to +20. So there's no need at all for something intermediate to take it part of that way. And then we're going to step up to the 45 to 65 degrees that's needed in the properties in one jump. And that actually is always more efficient, because you're not double handling through multiple heat exchangers. So that's our view on it, but yeah, aware of other people doing other ways. It's not something we're actively pursuing right now, though. Thank you for that question. That was a good one. Stuart, do we have another one?
Yep, I'll try and wrap 3 questions into approximately one. How many properties in a single development are required to make the system viable? And I'm kind of guessing Patrick can probably advise on the different sizes of developments he's done. And maybe Eman can help on the limitations and constraints and how many stories high can it operate at, and have there been any London new build or retrofit installations completed?
Okay, that's Patrick first on the site sizes.
Well, the site sizes we've done, I think the smallest has been about 10 units. To be honest, we apply the viability test to them with the numbers that are provided to us by Kensa in terms of the cost of the boreholes and the servicing of those sites. We apply the same appraisal to those regardless. Because our approach has been primarily on flatted properties, they have in the main part been groups that tie together of at least 10 and above. So that's the lowest we've gone in our particular applications at this stage.
I'd just to add to that on the cost, there's a significant cost in getting the drill rigs to site and set up. So to do that, to drill one short borehole, most of what you're buying is the setup and dismantling. So the economics do get better as you do larger sites, particularly above 20 properties. But as Patrick says, we can sometimes make financial arguments for smaller sites down to 10. So.
Yeah, I would just add to that, Matt, that the reason probably we could do that is the drill rigs are already in the area because we have a programme, and so moving them from one site to the other is less of an issue.
Yeah, so yeah, I think the question was about sites, but yeah, the size of programs does affect things as well, and particularly with drillers, they're more amenable to taking a small, awkward site with slightly higher costs if it's part of a larger program than they would be as a one-off. And Man, can you comment a little bit on some of the stuff around London, please?
There's been a number of really big projects that have happened in London, including the one that I mentioned earlier in Enfield. So Enfield Council have installed 600 ground source heat pumps across 12 tower blocks. Croydon Council are following with a large scheme there. We're also talking to a number of other London local authorities who are looking at retrofit scenarios. Just earlier today, I was talking about a new build with another London authority looking to develop a site adjacent to one of the tower blocks that already has ground source heat pumps. So in terms of it happening in London, yes, it's happening in London on a large scale. And what's really encouraging is that every single local authority that we've worked in London has come back for a second, third and fourth project. And they're always coming to us with larger projects. So the next project with Enfield is likely to be a 20-story tower block, which is replacing a gas system for various reasons, for example, fire safety, as well as obviously the retrofit and zero carbon potential. The technical aspect of it, we can develop that. We don't see that as a problem. Your limitations might be in terms of the available ground space or the curtilage of the land that's available in the tower block, but there's always lots of innovative and wonderful ideas that we've been able to come up with to work in even limited space. So you might be able to find an aquifer, you might be able to find sources of waste heat, especially in London. And certainly TfL looking at utilizing some of their ventilation shafts, and that's an area of interest for us as well in terms of developing a city scale 5G district heating network, which runs off low grade temperature. So yeah, there's lots of exciting work happening as we speak.
Thank you. Once there are a few technical aspects to the height difference between the highest ground source heat pump and the lowest on the same array. So in very tall buildings, we will typically split them up into sub-arrays with heat exchangers. So you've got sort of 10 stories at a time connected together. Okay, next one, please, Stuart.
Are there any ground types or locations that ground source heat pump cannot be installed? Or can you say they can be installed on virtually any new build, I guess, and retrofit social housing development?
That's another quick fire one. Nearly everywhere is the short answer. There are certain types of things that happen underground that can cause us problems. The most is if you've got high pressure water underground, so what they call an artesian aquifer. If they're mild artesian, they're not bad, but if they're very high pressure and very shallow, it can make it a bit of a challenge for us. So we almost everywhere, but there's the odd one or two places. I think we've got time for just one more question. Apologies to those whose questions we haven't got to, but we will, as we said earlier, do the written answers to those, and we'll distribute those out to everybody. So last one then, please, Stuart.
Okay, I'll try and make it a good one, and I think we'll maybe go for something that's maybe looking towards the future. So do Kensa see phase change storage as more useful for demand side management than battery storage? And if so, why?
It's my favourite subject, so I'll ask David if he wants to go first, but if not...
it's fine, it's your pet topic, you can
at the moment, phase change seems to be the front runner. Kensa, we don't mind. Either can work. The heat pump can either take electricity from a battery storage and then run when it's needed, or you can run when the grid has high availability to store the heat and then deliver that into the building, either heating or hot water when you need it. Right now, pound for pound, you can store quite a lot more energy in a phase change unit than you can in a battery, and the phase change units have longer lifetimes and can go through a lot more cycles than batteries. Batteries are improving hugely and very quickly, and you could argue that they're catching up a little bit, but right now, certainly for the next 5 to 10 years, we expect phase change to be the winners, but I'm sure both will play a part. Okay, so thank you very much for everyone listening and taking part. We hope you found it useful. Very special thanks to our panelists for their presentations and taking the time out of the day to do this. Please keep firing your questions in via email, and we'll try and compile them all and get them all sent to you in due course. Thank you very much.